So last time we analyzed the unique elements algorithm. We found that the best case input is one where the first two elements are the same, and that has a constant running time. We found that the worst case input is one that has no unique element, or that has all unique elements, all distinct elements, right? So no pair of elements is the same, and that has a quadratic running time. And the question is, what is there something in between, right? We have these kind of bookends that say one of them is the best thing you could see, one of them is the worst thing that you could see. But what should we think about? What should we think about putting in between, right? It's, in some sense, is there something in between best case and worst case that we care about? And so a concept that is commonly kind of inserted in between these is something known as average case. Average case. Okay, and so you'll see this concept of average case come up all the time, and I'd like to talk a little bit about what average case means and about some of the challenges that arise if you try to actually characterize the average case. So our question is, what is average case? Runtime. So the absolute wrong and naive approach to this is to say, so this is, I'm going to say in big red letters, the wrong answer is that you take the best case and the worst case and you sort of average them, right? And so here's the absolute incorrect approach, right? So the wrong way to do this is to say average is just sort of a blend of some kind of best and worst, right? So the wrong answer, right? This is the wrong answer, is that look we have this best is constant time, worst is quadratic, and so somehow that would average out to give you an average of, say, linear, right? This is wrong. Don't ever do this, right? Don't ever assume that the average case is something that you can eyeball, right? You can never eyeball the average case, right? This is the thing that you must take forward with you. And the question is why, right? Why is it wrong to try to eyeball the average case as being something that splits the middle between best and worst? Well, what does average mean, right? Average means on a typical input, right, what would you expect to see? And so typical is kind of a slippery concept. That's not something that you necessarily know what it means. And then expect to see is also a slippery concept, at least so far. It's not something you necessarily know what it means, right? And so the question that we really care about, is something like this. How likely are these kinds of inputs, right? So how likely is it that we run into a best case input versus a worst case input? So this is the question that eventually will lead to being able to analyze something about an average case, but it's something we need to have a grasp of early on. The question is, how likely are best and worst case inputs? Okay, so for example, suppose best case inputs are extremely likely. Right? Suppose that for some reason, somehow you've done the analysis or you've done a bunch of experiments and you've determined that best case is very likely. Right? If best case is likely, very likely, then it could be that you end up with a running time that is close to, with an average case running time or a typical case running time that is close to your best case. Then average case, and I'm going to say may be close to best case. Okay. If almost all of your inputs, and I say that in an informal sense, if almost all of your inputs are best case inputs, then that might push your average case close to best. On the other hand, it's important to understand something about how many worst case inputs it takes in your space of all possible inputs to tip the balance and make the average case much worse. So what I'm going to do is kind of a crude, rough analysis on this unique elements algorithm. This will probably spill into the next sequence of lectures. But I'm going to do a quick, crude analysis that'll give you a sense of some of the pitfalls that you run into in establishing average case. And it all ultimately boils down to this question: how likely are various kinds of inputs? Or if you operate the algorithm on some input, what are the statistical properties of the inputs that come to you, right? What do you actually expect to see? So here is a slightly formal description of what average case means. Okay, and I want to make it clear that it's important that you understand what average case means. But if I ever ask you to try to determine average case for something, I'll give you enough information that you can do it, right? It won't be something in this class that you have to decide what your assumptions are and such moving forward. So in this class, our focus will almost always be on worst case. And if we talk about average case, it'll either be informal or it will be very well structured so that you know what to do. So let me give you a definition or two, and this is just a definition for the purposes of this lecture to help you understand what's going on. So let me define T of A as the running time of this algorithm, and we'll just do this for unique elements, right? So the running time of the unique elements algorithm on the input array A. Okay, so this is time on array on input A. All right. So now let me define this script A of n. Yeah, that's fine. A with a bracket n. Now this is a script A, right? And so whenever you take a capital A and then you make it a script, the implication is that you're talking about a set or a family or something like that. So script A now, this is the set of all n element arrays. Okay? Set of all n element arrays. Okay, so this is a big set. I'm not going to ask you to try to write this set down. I'm not going to ask you to try to characterize this set. But it would be kind of a fun combinatorics problem to try to determine how many elements are in this set. Right? So I'll let you chew on that for yourself. If there's any combinatorics nerds out there, please do chase this down and get an answer. Of course, the answer will depend on what you assume, but I'll let you deal with that. So one more definition, and then I can actually formally define what average case means. So I'm going to define PA as the probability that if I draw an array at random from the set of all arrays, it is A. Okay, so this is the probability that array A, right, as the subscript there, is our algorithm's input. Probability that A is input to the algorithm. Okay, so there's our definitions, right? Those are our kind of our atomic pieces that we're going to be putting together. And so now I can tell you what average case means. Okay, so the average case runtime, T average, as a function of n, is defined as the following. It's defined as the expected runtime given the above terms, right? So the expected runtime on a random input. So it's the sum, and so if you've taken probability theory or statistics, this is something that you may have run into, but it's defined as the sum out of all arrays in the input space, right? So out of all arrays in this family of n element arrays, of the probability of getting the array times its running time. Okay, and so in math terms, this is I'm literally saying the average case running time for input n is the expected value of the running time of the algorithm on a random input. So this is the expected value of running time. So you say, oh, okay, I have a formula. There's a formula for this, so this is fine. If I have a formula, then surely I can just go analyze this. You know, slow down, easy there. Things can be more challenging than they appear, because immediately you can run into issues in trying to analyze this. The very first issues you'll see. So issue number 1, this set script A of n, right? The family of all n element arrays is huge. It's likely to be huge, right? So A of n is a massive set. So, and it has, depending on what assumptions we've made about things, this has at least factorially many things in it, right? This has an absurdly large number of arrays. So I'll just say it has too many to enumerate, right? Too many for us to write down. Too many elements. And here when I'm talking about elements, I mean arrays, right? There are too many arrays for us to do this well. So too many elements to enumerate. Okay. So we need to essentially compute a sum over a whole bunch of things that we can't even write down, right? There's too many of them to write down. So that's a problem, right? So what does that do? So how to evaluate the sum, or the expected value when there's too many things to write down. So that's point number 1. Point number 2 is where do we get these PAs, right? Where do the probabilities come from, right? So where do PAs come from? Right. And this is also non-trivial. And so the answers in practice are going to be, there's 2, right? One of them is they could come from experiments. So you could literally, rather than trying to evaluate this sum, you could just run your algorithm on a whole bunch of typical inputs, on things that seem to represent your input space, and then just tabulate the expected value of the running time, right? So and then you're not computing an expected value. Instead, you're determining an empirical average. So you could do experiments, and this is fine, right? This is completely appropriate as long as your random number generator has enough entropy in these things. You can actually do experiments to determine this stuff, or you could pick some assumptions and then actually do some analysis, evaluate the sum, and come up with some answers. And so in our next set of videos, we're gonna make some assumptions about the input space, and we're actually gonna do this, and we're gonna analyze the average case running time for a couple different sets of assumptions for this algorithm. For the most part, like I said, in this class, we're not going to focus too hard on average case running time, but I do want to give you a feel for what it means and what kind of rabbit holes it can lead you down.